Euler's method. I guess the first thing to talk about is it's Euler's method, not Euler's method. And the second thing to talk about, yeah, it's Microsoft Paint, but we're just going to draw on this for a little bit just to get ourselves together. Say, for instance, now, first off, what does Euler's method do before we start drawing on here? Well, Euler's method uses the slope to produce the next point given a starting point. So let's say we have a first order differential equation, and I know that the point, that the solution to that differential equation, I know the point is 0 minus 1. So I know the curve goes through that point. And I know at that point the slope of the curve is 2, the tangent slope of the curve. So that means that it goes through that point, that 0 minus 1 point, it goes through with a slope of 2. That means if I move over 1, I would go up 2. If I move over 2, I would go up 4. If I would move over a half, I would go up 1. So we're going to choose to move over a half. So with a slope of 2, if I go over a half, I would go up 1, and so I would end up at this point here, at the point 1/2, 0. I went, that's supposed to be a straight line. I moved over 1 and up a half. So how did I get this new point? Well, the x value of this new point is a half, and I chose that. That's going to be our h. That's going to be our step size. We're choosing to equally space these points out. A half, so the next one will be at x equal to 1, then x equal to 1.5, etc. Now, I get to choose that. Why would I choose a small step value? Well, if I choose a small step value, then my answers will be more accurate. In other words, the points that I generate using Euler's method will be closer to the real points of the actual solution. That's good. But the bad thing would be the disadvantage, let's say, of choosing a small at h value, a small step size, is that if I take small steps, it takes me a long time to get somewhere. So if I want to figure out what's the y value when x is equal to 3, which with an h, with a step size of a half, I'm going to need 6 iterations of this method to get there. If I took a bigger step, maybe made h equal to 1, I can get there in 3 steps, but I give up accuracy. So in general, it's a compromise. Small steps, takes a lot of small steps to get to the desired answer, but it's more accurate. Big steps is faster, but not as accurate. Anyway, so I'm at this new point. This is the point 0, 1. And if I recalculate the slope here, say I recalculate the slope here, and I get m is equal to, I get the tangent slope is equal to minus 1. That means if I move over 1, I would go down 1. But I'm moving over a half. So if I move over a half, I would go down a half. So the next point should be here, that's a huge point, at 1 minus a half. So how am I getting this point? Well, the x value is all equally spaced. The x values are going to be 0, a half, 1, 1.5, 2, etc. It's the y values that I'm calculating. And how am I doing that? Well, I'm getting my new y value by taking my old y value plus hy prime. That's the algorithm then. So let's get back here, Euler's method. We've got a differential equation. So when I was drawing in Microsoft Paint here, I was just saying, oh, the tangent slope is 2, the tangent slope is minus 1. How would I actually be calculating those slopes? Well, I have a slope formula. I have a y prime equals a function of x and y. That's my differential equation. So the problem starts with your differential equation, your slope formula, and an initial value, an initial point on the curve. So I use this recursive formula. The x's are all equally spaced. The new x is equal to the old x plus h each time. The y's, the new y is equal to the old y plus h times y prime. This is your slope, this is your y prime, your f of the x value that you're plugging in. Let's let's use this to find points that are close to the real solution of this y prime is equal to x plus 2 over y. All right, I'm choosing h is equal to a half. So I'm interested then in what's the approximate y value when x is equal to 1.5. I'm starting out with x equal to 0. I'm going to have to do 3 steps then to get to the x is equal to 1.5. So here are my x values already laid out. 0, a half, 1, 1 and a half. That's using this formula here. New x is old x plus a half each time. The first y value is given by the initial condition. So now with the yellow, that's the given values. I calculate the tangent slope at the point 0, minus 1. Essentially, I'm plugging in 0, minus 1 into the slope formula, into the differential equation, and I see that the tangent slope at that point is minus 2. That means if I move over 1, I would drop down 2. But I'm moving over a half, so I drop down 1. So then my new y is equal to my old y plus hy prime. New y is equal to old y plus hy prime. I was at minus 1 and I'm dropping down an additional minus 1. So now I'm at minus 2. Here's the new point. This new point, a half minus 2, now I can start the algorithm again. I can find the tangent slope at that point, plug in x is equal to a half and y is equal to minus 1, and I calculate that the slope is equal to minus 1.25. That means if I move over 1, I would drop down down 1.25, but I'm moving over a half, so I drop down 0.625. So new y is equal to old y plus hy prime. There's my next x value and y value, respectively, x value and y value. Replug those two xy points into my slope formula, recalculate the slope as minus 1.14 and change. I go over a half, so I drop down half of this amount, and my new y value is equal to my old y value plus hy prime. Now there's an approximation. My approximation is when x is equal to a half, y is equal to minus 3.19. That's using Euler's method. How accurate is that? Well, in this instance, we can actually solve this. Let's get the real solution. So here I am getting the real solution. I'm using separation. I multiplied up the y, multiplied up the dx, integrated both sides, the y side with respect to y, the x side with respect to x. I'm using that separable technique. There's the constant. How do I figure out the constant? I've got the initial condition. I plug in the initial condition, solve for y for my explicit. Notice when I square rooted, I purposely took the minus. When I square root plus minus square root, I took the minus. That gives me a constant of a half. Here's the solution. It solves this differential equation and goes through the point 0, minus 1. How close am I? How close is my answer? Well, what's the actual value? When x is equal to 1.5, what do I get for a y value? I'm getting minus 3.04. The actual real answer, my approximation, was minus 3.19. All right, so it's not perfect, but it's not too bad. If I wanted a better answer, what I should do then, if I wanted a better answer, would be to make a smaller step size. So here I'm interested in 3. Here I'm interested in 3. And when x is equal to 1.5, there's my Euler's method. There's my actual with a step size of a half. In this case, let's make a smaller step size of 0.025. No, 0.25. So we'll just do a quarter. So now I had to do more steps to get up to 3. but I can see that my answer is closer to the real value, right? Double the steps. So 3 minus 3.1, and that's the real answer here. Let's take an even smaller. If I take 0.1 of a step, oh, then I don't actually get there. So pretty close. Right now I'm in the third decimal place. If I take a look at the picture that I'm making, there's Euler's answer and there's the actual answer. The points lie pretty well on the actual curve. Let's go back to that 0.5. Now I can see some separation of them. And I'm taking steps of a half, so I mean I get all the way up to 7.5. Euler's method. Most of the time, if you're doing this, you're using a computer, so step size or a spreadsheet, or coding this up in Java or something. So step size is not a problem. Make it crazy small and just make the computer do a lot of iterations. As far as doing this for a course, you would only ever do Euler's method for a question if they asked you to use Euler's method. It's a numeric technique.